So thank you everyone for coming to the second part of our Grounded webinar series for 2021. We have three panelists to join us today. So we have Associate Professor Matt Hill, Associate Professor Akshat Tanksale, and Romalya Ranasinghe. Just to give each of our panelists a brief introduction. So Associate Professor Matt Hill is the current Deputy Head of the Chemical Engineering Department at Monash University. He is an academic with a joint position between CSIRO and Monash. He works on metal organic frameworks, and he has shown that these chemical compounds have great potential in capturing CO2. Then we have Associate Professor Akshat Tanksale. He is also another academic within the Department of Chemical Engineering at Monash University. So he leads the Catalyst for Green Chemicals Group, which conducts research that includes converting CO2 into chemicals and fuels. And finally, we have Romalya. Romalya is a final year chemical engineering student at Monash. She is currently the VP of the SMIS, which is the Student Society of Chemical Engineers. And she works as a technical assistant for one of the Woodside Monash Energy Partnership projects, which looks at direct air capture of CO2. So just to give everyone a brief of the format of the webinar. So each of our speakers will present for about 10 minutes. Then we'll have about 5 minutes of questions for each panelist. And then at the end, I'll open up the floor again for about 10 to 15 minutes of questions in case you miss out in those 5 minutes. So Matt, if you would like to present first.
Yeah, thanks, Brian, and good afternoon to everyone. And I guess today's you're hearing three different presentations, but really it's one big project where we're all working together in one way or another. And what we're looking at is this concept around, is it a good idea to try to capture carbon dioxide directly out of the air and then convert it into other valuable products? So the chemistry here is well known, but making this a viable technology, that's the big challenge here. And so, as Brian mentioned, I have a joint position between CSIRO and Monash, and this project is very much joint between the two organisations. And so what I'll do is I'll give you just a very quick history of what we're up to with trying to capture CO2 directly from the air. And based on that, Akshat will then be able to tell you whether that's feasible for him to then convert that CO2 into other molecules. And Romalya has been looking at with us what this might look like if you were to scale it up to an industrial scale. So just moving through, Brian said my team work on metal organic frameworks, and in essence, a metal organic framework is a very, very porous material. It's kind of like a big sponge, and you can have these tiny holes. You can make those holes to have different surfaces in there so that different molecules are attracted in, like a sponge soaks up a particular molecule. And you can see here, this is a bit of a summary of the sorts of things that our group do when we're looking at using these molecules for all kinds of different applications. And we actually started in this area in carbon capture. Originally, we were looking at capturing carbon dioxide from flue streams, whether it be from a coal-fired power station or a concrete plant or a natural gas station. In all of those cases, the CO2 concentration we're talking about is in the several percent, maybe from 3% to 15 or 16% carbon dioxide present. And so the idea is that can these metal organic frameworks slurp up the CO2, but not everything else that's coming out of the stream, which is in the large part nitrogen plus some reactive things like sulfur and nitrogen oxides. And so we had shown in the lab that this was quite feasible, but of course fits into a much bigger economic question around whether those technologies of the future and whether we have a carbon tax or not. And, you know, I don't need to take everyone through the last 15 years of Australian politics, but that's been the number one issue. I think a carbon price has seen 5 different prime ministers in this country. So we've been right at the wave of all of that. So one of the things that was most interesting to us was, given that we got so good at capturing carbon dioxide at that 3, 4, 5, 10%, is it feasible to do it directly from the air? Now, of course, we all know that the amount of carbon dioxide in the air keeps going up and up and up. It's a bit over 400 parts per million right now, but that equates to about 0.04%. So, some people might say, well, that's such a small number. Why do you even care? Well, 0.05% of alcohol in my blood means I can't drive a car. So we know that very small amounts of molecules have very, very big effects. And that's what we're seeing with carbon dioxide. So there's 400 parts per million. It's a significant thing. We need to do something about it. But of course, it's also a challenge from a separation science standpoint that only one in every 2,500 molecules that are in the air is a carbon dioxide molecule. And so we need to efficiently find that molecule, capture it, and then release it from whatever we've captured it in so that we can give it to Akshat. So some of the applications that you could use CO2 for and are already used are on this slide, as you can see here. And believe it or not, Australia is a net importer of carbon dioxide. So at the same time as us making so much carbon dioxide, we still buy it in on a boat, somewhere between $300 and $800 per tonne. So those are the numbers you want to remember. $300 to $800 per tonne is what the current market price is for carbon dioxide. So it can be used in a greenhouse, and Romalya has been thinking about this, about whether putting more CO2 in a greenhouse makes the plants grow quicker, increases the yield. Dry ice, of course, we can make that directly. Carbonating beverages, especially in remote locations where shipping the carbon dioxide there is not feasible. Akshat will talk about conversion into other molecules, and renewable methane is one example of that. And another one, of course, is fixation within concrete. So what we did joint with the CSIRO, we started about 4 years ago, which was to look at can we find a business case for doing this? And this is where we started to understand what the prices needed to be per tonne of carbon dioxide captured. And that set us a technology challenge of whether we could get a material that's below that. So what I'm going to show you now is what we know at this point in time about the cost of doing this. And so we, a couple of years ago, we got a grant to then build a prototype demonstrator, which is TRL6, which is a large-scale unit so that we could actually prove some of this technology. I'll just show a couple of the results to introduce it all. So, of course, here's that other slide. Australia, we import CO2, but we're also one of the highest emitters per capita of CO2. So if ever there was a country that needed to work on this, it's us. And so when it comes to that economic feasibility, we worked out that there was one number that was most important, and that is how strongly does whatever method you use to capture the CO2, how strongly does it bind with your CO2 molecule that you're capturing? So the more strongly it binds, that's more energy you have to put in to release that CO2 molecule so you can regenerate your system. And so you just think of this as money. So the higher that these are, the bigger the money. Now, these are other competitor companies that are present on the market at the moment. And the thing about our technology that was exciting was that it's a much lower binding energy. So from a feasibility perspective, that's exciting, but we're still trying to get that 1 in 2,500 molecules out. So we need to do a few other tricks because we're not grabbing onto it as strongly as we might otherwise be able to. So here's our unit. We called this unit Athena. Athena being the Greek god of science, and we're dealing with air, so that's what we came up with that name together. The TRL6 prototype that I mentioned. And essentially what we did was to build a very, very special MOF nanocomposite and put inside here in a series of absorption columns and cycle it again and again. And you can see here, we just need to get to about 80 degrees to release that captured CO2. So this is a plan of what's inside at the moment. This is in the New Horizons building here on campus. We have 9 absorption columns filled up with MOF nanocomposite. It takes about 40 minutes to saturate one of the canisters. You've got to blow a lot of air through because there's not very much CO2 in the air. And it takes about 20 minutes to regenerate. So to heat up to 80 degrees, release the CO2 that you've captured, and then cool it back down, ready to go again. So at any one moment, we have 6 of the tubes filling and 3 of the tubes empty for that reason, because of that 2-to-1 ratio. So we ran this for a while. Initially, we ran with one tube, and I sat there for the whole day with a Microsoft Excel spreadsheet and wrote down every number. And then 3 months later, we had it automated, and we did 1,100 cycles in a week. But it just took us a bit of time to get that right. And then from that, we were able to start to pull out some of the data. And it's just a very quick talk today. So I'm just showing you a couple of quick data points. Here's one of the key ones is the energy consumption per kilogram of CO2. So that's the number we need to know because that's the operating cost of running that. So we need about 1.6 kilowatt hours for every kilogram of CO2 that we get our hands on. You can see the unit's very stable. Here's 200 cycles, 3 different modules, different packing, so they had different amounts of CO2. But you can see the best fits there that over several hundred fills are essentially unchanged in its performance. We then produced the materials, and I'm showing you here a photo of the large-scale chemical manufacture. So this is now happening just down the road in Noble Park at a company called Bora Molecular, and they're making about 100 kilograms per week of the material and getting that cost significantly down as well. So based on all of that, we were able to put together a bit of a summary. So that 1.6 kilowatt hours per kilogram, it depends on what your energy costs, of course, if you get it from solar panels or waste heat, or you buy it from a coal-fired electricity station, all different options. And that gives you a number somewhere between 45 and 200 US dollars per tonne for your operating costs. So remember I said that the price that we pay off a boat today is between $300 and $800 per tonne. So it's between 40 and about 200 operating. And then Romalya will talk a little bit more, but one of the headline figures we know at this stage is if we were to build a bigger plant, and here's a outline of what Athena 2.0 might look like, that could capture about 100 tonnes per year. That comes in with a capital cost of about $175 per tonne to do that. So you have to add that on to the operating. So we're somewhere between $220 per tonne and maybe about $400 or $500 per tonne total cost for doing a CO2 capture directly from the air. So we're at that point. You might say, well, okay, it might be cheaper, it might not be cheaper than buying it off a boat. The bigger question, of course, is that's the cost. What's the price, though? So to the world of having less CO2 in the air. And so we're at the sort of tipping point of the feasibility. And as we scale it and scale it and scale it, maybe we can bring these numbers down even further. But at this stage, our conclusion is that it's not a stop. It's not a no. It's at least better than what it currently costs to buy. And how much better is really what we need to do. So that's enough from me in terms of an overview. And I'll be happy to answer any burning questions that have come up immediately.
Yeah, so if anyone has a question to ask, please feel free to use the Q&A function and we can get that through. I'll get it started. So Matt, what kind of drew you to using MOFs for CO2 capture? Like what kind of attracted you to the potential of this technology for this purpose?
Well, I guess it's that fundamental thing of the low energy requirement. So the reason that all of those other examples are so much higher is they're doing a chemical reaction. So they're actually forming a new molecule that has CO2 inside of it. And that requires a much higher amount of energy. And we thought with MOFs, that weaker interaction would give us a chance of making it more feasible. And we sort of backed ourselves that with MOFs, with these very small holes, we could use all the other tricks of the trade to make the CO2 selective without having to use a lot of energy to do so.
Yeah, awesome. I'll just fill out another question. So we've got one from Nimrod. So how do you scale it up to capture CO2 from alumina refining or iron and steel?
Yeah, so I guess in terms of alumina refining or iron or steel, it's a little bit of a different challenge. So those situations, we have what we call a point source of emission. So there's a whole bunch of CO2 being emitted out of one pipe and its concentration is much, much higher. So we can use a different type of system because it might not sound different, 0.04% to say 10%, but as a ratio, that's several orders of magnitude different in terms of the gas composition. And so what we know today is the best way to capture CO2 at those levels is actually to use a membrane, which is like a filtration technology for those much higher scales. And so that's another area of research that we're very interested in.
Okay, awesome. We've just got one last question from you, right? Does that mean it is even cheaper to get CO2 from point sources?
Yeah, absolutely. So because you have so much more CO2 per unit time, the feasibilities are much lower. If you're unlucky enough to be in one of my fourth or fifth year classes, I do a case study of this when it comes to capture directly from a point source. It is as low as $23 per tonne to do that, which is very encouraging. For those of you who lived in Australia long enough, the interesting thing was that the carbon tax that was put on us was $23 a tonne. So it was the same number. So it basically would have been free had we kept that policy.
Okay, awesome. We have another question, but we might move on to Akshat and we'll come back to this question at the end.
Okay, thanks.
So Akshat, thanks again for that presentation, Matt. Akshat, if you would like to go next.
So today I'm going to talk about what happens after where Matt left off. So you can capture CO2, but unless you can do something with that CO2, we don't have a solution which is sustainable for long run. Okay. So on this slide, I'm just presenting an overview of what can be done with that CO2. So Matt mentioned obviously you can capture CO2 from air. So that's at the bottom there. You can capture CO2 from that point sources, which is burning of your fossil fuel or industrial processes, and some of the underground deposits. So when you extract natural gas, for example, the CO2 that was in that natural gas also comes off. So that's the emission of CO2 that was kind of sequestered by nature for us, and we've now pumped that back into the atmosphere. There is some biomass burning happening as well. So that's not such a big problem because biomass in itself was grown using the CO2 that was in the atmosphere. However, we're burning far more biomass than that we are growing. So the amount of deforestation that is happening is outpacing the reforestation efforts. And so that is also a big problem for us. Anyway, so all of these combined, once you've captured CO2, there are two pathways essentially. And I'm going to talk about the non-conversion pathway first because we're not working on that. And at least my group is not working on that. There might be some groups which are working on this in Monash. So this is called as direct use, where the CO2 is used as the molecule CO2 was captured without the conversion part. So this can be used in multiple ways. You can do yield boosting of greenhouses, which is something, in fact, that Romalya and Matt are working on with us, where you provide the CO2 into a greenhouse, which increases the productivity of agriculture products. You don't need too much CO2, only about 1,000 ppm will be enough. You can likewise grow algae, and that algae can be used as a source of protein or a source for energy. But either which way, both of these will eventually lead back to CO2 going back into the atmosphere, because if you've grown biomass, you will consume that biomass, whether as a food product or as energy product, that CO2 will eventually be released back into the atmosphere. So you get two uses out of that CO2, but in the end, it's not a long-term solution. You can make fertilizers, which in the end again boost the energy, the crop yield, but again that CO2 goes back into the atmosphere. Now CO2 can be used for what is called as enhanced oil recovery. So for oil which is deep underground, which obviously pressure is much higher underground than it is at the surface. So to take things out, things flow from high pressure to low pressure. So the oil will come out regardless if you don't pump CO2 back into it. But you can increase the recovery of the last bit of oil that is still left when the pressure drops in the well by pumping CO2 in that well. So this is the enhanced oil recovery. You can do decaffeination of the obviously coffee beans by CO2 extraction. You can use CO2 for dry cleaning. None of these solutions lead to a long-term solution for CO2 again. You can use CO2 as refrigeration fluid or supercritical power systems. And there are many other examples like CO2 in beer and soft drinks. Again, very short-term solution because you burp it out. So I'm going to then talk about what can we do to enhance the CO2 life cycle, lock it away for a little bit longer than a few days. So Matt briefly mentioned methanation. So this is a process where you produce methane using CO2 and hydrogen. In this case, the hydrogen would come from water electrolysis. So you're using two essentially renewable sources. The energy to make that will come from renewables, so solar farms or wind farms. The process of making methane itself is a bit exothermic, so you produce excess heat as well in that process. Whereas other chemicals like methanol and diesel and gasoline can be made from CO2, but they are endothermic processes and they require a lot of energy. Methanol process is a high pressure process, so you need energy for both compression and supplying heat to the reaction. So again, this will be successful only if we can provide renewable electricity to make these fuels. Now, again, you would say that, well, if you make fuel, then you are actually going to produce CO2 eventually. But in this case, we are actually replacing the fuel that was in supply from fossil resources, right? So we are actually displacing the CO2 that would eventually come out of the ground. You're taking out fossil fuels from the ground, you're burning them to produce CO2. Here we are actually taking the CO2 and then producing fuel. So we are displacing or substituting part of the fossil fuel that was going to be burned. So it gives you a little bit of an advantage. Again, it's not a long-term solution unless we can stop all fossil fuel mining. This will not bring down the current levels of CO2 in the air, but it might slow down the excess CO2 in the atmosphere, and it might actually start to stabilize a bit. What can be done to have a long-term solution of CO2 in the current at the current levels of emission that we are producing? We are unlikely to meet the 2 degrees Celsius temperature rise in the next 50 odd years that the COP21 agreement in Paris. What we need is negative emissions. So CO2 must be converted into some chemicals which are not going to be released back into the atmosphere. So you could convert CO2 into chemical intermediates like methane and methanol, but then these intermediates are further converted into other products. So methanol is a feedstock for many different chemicals like formaldehyde, olefins, and a few other things. So they can be made into polymers and plastics. Now those actually last much longer than few days cycle that fuels last. So they can actually be in a solid form for decades or hundreds of years. Likewise, you can make building materials out of it. So you can take CO2 to make filling materials like aggregates, and you can make cement and concrete and lock that CO2 away in the buildings. Now, in fact, concrete making process is currently a net CO2 emitter, a huge emitter of carbon dioxide. So if we can somehow reverse that process and lock CO2 into cement and concrete and then into the buildings, then again, buildings last for hundreds of years. So that's potentially a negative emission solution. So this process is called as mineralization. So you take a mineral oxide and then you carbonate that mineral oxide so that you have a CO2 locked away as carbonates, and then those carbonates can go into bricks and so on, and can be locked away into building material. Okay, so how do we do that conversion then? Okay, so there are many ways. So I've shown here in a small cartoon. So you've got either direct air capture or industrial point source capture of CO2. And then you do some processing. So you can do mineral carbonation. So this is called as utilization processes. There are three major pathways. Mineral carbonization is where you get the construction materials. Chemical conversion is where you're doing catalytic reactions of some sort to convert it into intermediates, chemicals and fuels, which is where my group is mainly focused on. So we've developed a couple of new processes for converting CO2 directly into formaldehyde, which currently comes from methanol, and that methanol comes from natural gas. So if we can bypass all of that process and make formaldehyde directly from carbon dioxide, then formaldehyde is used in many chemical industries. Mostly it is used as a resin in particle chip boards. It's used as in making polyurethanes and other foams and plastics. So they are actually used in making stuff that are solid, and so can stay in the solid form for a little bit longer than a few days. Then there are biological conversion pathways. So instead of using a catalyst, you use microbes, either enzymes or whole organisms, to convert CO2 into, again, some intermediate chemicals or polymers, even polymer precursors. So I'm leading the carbon capture conversion utilization theme of the Woodside Monash Energy Partnership, and biological conversion is one of the pathways that we are very interested in. So I'm working in collaboration with Victoria Heritage, who is a professor in our department, and also some startup companies like Bondi Bio. I've got finally a project student right now who is working alongside Bondi Bio to look at biological conversion of CO2 into astaxanthin, which is a chemical which is very high value. It's currently sold for around $5,000 to $7,000 per kilogram. So if we can get such a high value chemical out of CO2, which has got no value, apart from obviously the inherent, the amount of money that you need to put in to capture that CO2, we can actually make the process more viable, because fuels inherently are quite cheap. And so if you want to go from CO2 to fuels, there's always an economic problem where you are putting in more energy and more money to make the fuel than you can actually recover from that. So if you can make high value products, then you have a path to market. Obviously, consuming all of these chemicals and fuels might produce some short-lived use and release the CO2 back into the atmosphere. Some of it, which we might be able to recycle if there are point sources, so such as fuels. If you are making fuels out of CO2, then that's a short-lived use. If it's used in transportation, then that CO2 goes back into the atmosphere. If it's used in a stationary power, then that CO2 can be captured and recycled. What we want is really these long-term uses, like polymers and plastics, which can stay in the solid form for a little bit longer. So that's in a nutshell what we are trying to achieve here with the CO2. And I hand over back to Brian. If you have any questions, I'm happy to take that.
Yes. Cool. Thanks for that, Akshat. That was an interesting presentation. Again, if anyone has any questions, please feel free to add them into the chat or the Q&A function. I might just lead off and start with one. So Akshat, traditionally, a lot of the chemical pathways for CO2 conversion relies on a lot of energy and heat, which we typically derive from, fossil fuels. How is, this particular research area kind of overcoming that challenge so that we can kind of integrate more renewable energy into the process?
Yeah, so renewables integration is the main challenge, and electrification of chemical industries is what is needed, so that traditionally we have said, when we teach chemical engineering today, we say, well, heat is much better than electricity in terms of heat transfer. So wherever we want to achieve heat transfer, we use a heating or a cooling fluid rather than electric power, because traditionally that electricity comes from burning coal, and there are inefficiencies in that power generation. It's only about 30% efficient, unless you go for supercritical, which then starts to approach about 40% efficiency, and then there are transmission losses and whatnot. So in the end, the energy usage that we get is a factor of 3 less than what primary source of energy was. right? So if you take, for example, 300 kilojoule energy from primary source, which is coal, only about 100 joule is eventually transferred to the process, which is not what you want. But if that electricity comes from renewables, then those efficiency losses are not there. So in a nutshell, we want processes which can run on electricity, which is counterintuitive to how chemical industry is currently built. So there will be a lot of retrofitting required of current processes, or new process will have to be built with electric integration in mind. So that's where some of our research is as well. We are working on CO2 dry reforming of methane, which is a high temperature process that works around 800 to 1000 degrees Celsius. But we are using induction heating to provide energy to that reaction.
Okay, awesome. Thanks, Akshat. So we have one question from Nimrod. So fossil fuels provide energy as well as the CO2 for conversion. What is the current scenario in terms of costs associated in the process?
Cost of CO2, see, there are no current chemical processes which take CO2 in large amount. There's methanol, some of the methanol process actually can take CO2. Current ones use CO2 to shift the chemical equilibrium of the reaction. And so when natural gas is combusted or gasified in this case into hydrogen and CO2, some of that CO2 is utilized to make methanol, but that's a very small amount. I mean, vast majority of CO2 goes into the atmosphere. So currently we're using fossil fuel only for energy, not for CO2. In the end, we want CO2 sources for chemicals and plastics industry from point sources, which lead to zero emission to atmosphere.
Okay, awesome. We have another question from Nimrod, but we might circle that back to that, just to be conscious of time. Romalya, would you like to present next?
Yeah, hi. Let me share screen. So this is just the introduction to the project that I've been working on, that Akshat and Matt have been supervising me on. So we're working on, like they said, capturing carbon dioxide directly from the air. So our focus here is this Athena model that Matt showed you earlier. This allows us to directly capture the carbon dioxide from the atmosphere. And then later, like Akshat said, we can either store it, we can use it as fuel, chemical feedstock, greenhouses. And my target in this project is to particularly look at how we can use it in greenhouses. And this Athena model currently captures 6 kilograms of carbon dioxide per day. It absorbs the CO2 into the bed and then it regenerates it. So how this works is they use the cycle called a temperature vacuum swing adsorption process. It's a little technical term, but it's actually simple if you read the paper. They use a porous nanocomposite, the MOF that Matt mentioned in his speech. And this separation is done by selectively absorbing the CO2 over all the other components in the air. So nitrogen, oxygen, water are not usually that absorbed into this bed. That's why you only have the CO2. And we only need a relatively low temperature to regenerate the CO2 back out. And hence that is why the cost of energy used for this small scale model is not too high, which is good news for us. So my project objectives is to focus on upscaling this current process that produces 6 kilos of CO2 per day to possibly 10 tons of CO2 per day, or even more than that. So we're currently looking at maybe expanding it, but for now the focus is to see if the 10 tons CO2 per day is a feasible model, how should we change it, etc. So like I mentioned, I will also be looking at observing factors affecting the yield of CO2. So there have been a few challenges that have been met along the way. So my whole point in this project is to come up with feasibility studies, model it on softwares to see how we can change it, how we can better it, etc. So overall objective is to increase the percentage of CO2 in a greenhouse to promote plant growth. And like Akshat said, this would only require a smaller percentage of CO2. So even if we want to go for higher than that, then there should be an upscaling process that says, okay, look, we can look into this, something like that. So in terms of the technical work that I have done since I started this project last summer, I've been using a few softwares, and you can see I've attached a few screenshots here. So basic purposes were just to check for general mass and energy balances, just to see if the small scale model, first of all, if we can model it on a software correctly, and then look at how we can upscale that small scale model on the software. And for this, I've had to curve fit certain data that we have in terms of the adsorption isotherms to fit it into the models that are there in these softwares. So those are some of the graphs that you can see there. And at present, the project's progress has been looking at modeling the process flow diagram for upscaling. So Matt showed you the small scale existing model and how you had 9 of those beds in one row and everything like that. So we've decided for the upscale model, if we were to build it, then we would have to make the beds bigger and then have only 4 of them. So 2 of them would be adsorbing at the same time, whereas the other 2 would be desorbing, and it's a whole cycle there. So for this process flow diagram that I have created, we have calculated rough cost estimate, which is the cost that Matt mentioned earlier before. And we focused on maybe branching out to capturing other components, but for now, the main focus is carbon dioxide. And we've also evaluated the potential of air cleaner technology in other practical applications, like where else can we use it? And that's the whole point of Akshat's presentation. He was talking to about how CO2 can be used anywhere. So these fans that you can show, these blowers, actually, if I can just show a picture. So those are the large industrial fans that are used by a company called Climeworks. They use a different process to ours, but their end goal is to capture CO2 by directly blowing it through the air. So those, or like bigger fans, would be the size that we would have to go for. So that's just to get you an idea of how big this would be. And so Brian asked me to introduce how I became interested in this area of work, since I'm just a student. And honestly, when I was in my second year, I had to stand outside Akshat's office a lot when I was waiting for him to call me in for meetings. And he had that sign that you see here on his door. And I was always wondering what it was. And then I was curious about it. So I read up, and he looks at catalyzing the conversion of biomass into useful products and converting CO2 into useful products. So I thought, hey, this sounds like something that's very sustainable. It will enhance the quality of life. And I reached out to Akshat, asking to be a part of this. And yeah, thank you for letting me. So again, like Akshat mentioned, he looks at negative emission technology, and basically the aim of reducing the global warming level to at least 1.5 degrees below pre-industrial levels. So if this project were to be upscaled properly, then it would reduce it to at least 2 degrees below the industrial levels. And like the United Nations decided, this would be way below the goal that they set. So this is a very important project in terms of enhancing the quality of life. And we look at like carbon emissions trading. In terms of how I use my skills and knowledge as a student to be a part of this project, these are a few of the softwares that I have had to use in my time. So at Monash, they don't teach all of these software. So there was this one software called Aspen Absorption that I had to learn, which was also fine because I had to reach out to my supervisors, ask for guidance from them. And also, I would like to state that the design units that we have for chemical engineering have been extremely useful for me to understand how to do a basic cost estimate, a rough process flow diagram designing, and skills like that. And yeah, thank you for listening.
Thanks for that presentation, Romalya. It was very interesting and insightful about the work that you got to do. So if anyone has any questions for Romalya, again, please feel free to put them in the Q&A or the chat, and we'll ask it through. So just to get started, Romalya, so how did you find the experience as a student, and like how did you feel you could actually, or what you were contributing to, I guess, this project overall?
Yeah, so when you are a student, the projects that you get are like pretty, they're very thought of, and like, you know, they're things that the lecturers have put a lot of thought into, but this is an ongoing project. So that means there are a lot of like challenges and hiccups that come up along the way that I've had to learn firsthand, just because when you do a design unit, that's not something you really meet with. So as a student, I've really learned that projects are not like a easy path to, like, you know, get to the end goal. It's just like, yeah, but it's really been an enjoyable experience, and I'm learning a lot. So I really enjoy everything.
Okay, awesome. I guess I think a lot of the people attending this webinar are students as well. What kind of advice would you give to get, if students are interested, to get actually involved in these kind of projects, or how to go about it? Based on your own experiences.
Yeah, based on my little experience, I would say look at the kind of topics that interest you and read up, because the research team at Monash really do look at a whole range of topics. So if there's anything that interests you, just reach out to a lecturer who is teaching that or is working on it, and then they will guide you where to go with it next.
Okay, awesome. Thanks, Romalya. So we might circle back to some other questions now. So we had a question from Stefan before. I think this was directed towards you, Matt. So we asked, do the economic calculations include a future price on carbon, which is already in place in other countries? Feel free to answer if Akshat or Romalya, you have input on this as well. So I think it may kind of cover what you guys talk about.
Well, I guess our calculations are on the other side of the profit and loss sheet, where we're looking at what the cost of doing this is, and you would offset that against a carbon price rather than sort of adding it on top. But I can say that I know many companies who are in the energy production space are starting to discipline themselves with their own business plans for new projects and so on, where they're putting in a carbon price to help assess the feasibility. So there may not be one in this country today, but as mentioned, they're in many other countries already. So it's certainly a very big part of assessing feasibility of any new project.
Okay, thanks, Matt. And I guess to add on to that question, as a part of the these kind of economic calculations, does it kind of take into consideration how renewable energy may play a role and how it could eventually reduce in cost compared to, I guess, fossil fuels?
Well, for our specific use case, that's been front and centre because it's the cheapest form of electricity is renewables at the moment. So we're very much looking at that as to whether you would install that or whether you could get access out of the grid specifically. So in terms of those sorts of cost calculations, the US Department of Energy has set a lot of guidelines for that, because ultimately, you know, I could make up any sort of number and say if I did A, B, and C, it would give me a great answer. But the US Department of Energy has some rules around that. So we've been very keen to follow those just so that we're comparing apples with apples.
Okay, no worries. Thanks for that. So we had a question from Nimrat previously. So we asked, is there no scalable application of CO2? I think this was in regards to his question before about using fossil fuels to provide the energy for CO2 conversion. So Akshat, if you
look, at the moment there are no commercial processes for captured CO2 to make any useful product, because CO2 is at the bottom of the thermodynamic well, so to speak, right? So to take it out of that well and do something useful with it, most of the products are, you know, well above the ground level. I mean, you know, if you look at the energy, you know, balance, CO2 is at the bottom of the well, and then most of the products are well above the ground level, so to speak. So to put that in perspective, we have to add energy to it, and therefore it's a chicken and egg problem, right? You need energy to convert CO2, and that energy currently comes from processes which produce CO2. So at the moment, it's not a zero-sum game. So we need really solutions for renewable energy. So we call these enabling technologies. And so unless those enabling technologies progress simultaneously with the conversion processes, of course, we need better conversion process, better catalysts, which are going to do the conversion in lower energy cost. Then then only we will have a sustainable solution. It's not an easy challenge, certainly not for faint-hearted to do working on CO2 conversion technologies for industrial application. But I think if we were to survive as a species, we need a solution for CO2 capture and conversion, and so we can't stop working on that.
Okay, awesome, thanks for that. And I guess kind of to lead on in that question, this is, I guess, directed to all of our panelists. What areas, and I guess CO2 capture and CO2 utilization is a particularly challenging area, especially through chemical routes. But what areas and kind of potential of development do you think students could actually work and contribute to actually help this area grow and develop in future?
So if I can very quickly plug in, thanks for that segue. So we have this Monash, a new Monash team, which we tentatively call Monash CO2 capture and conversion, which has just sent out a call for expression of interest for leadership. We're just in the process of selecting the team leaders, and then wider team will be set up so that we can have a team which works directly in a student team, which will work on CO2 conversion technologies, possibly both capture and conversion. And the aim is to go for the X prize, $100 million prize for CO2 conversion, capture and conversion. The challenge there is to be able to demonstrate at 1 ton per day scale, which is significantly bigger than what universities are working on. And also to be able to do it for at least 100 years, so which means the CO2 that was captured does not go back into the atmosphere for at least 100 years. Right, so that's the challenge, but I think it can be done, and we have made our efforts to start forming this team, and the students can contribute directly into research. We'll probably be working on real applications in the labs to progress this agenda.
Thanks, Akshat. Matt and Romalya, do you guys have, I guess, insight into where students can actually contribute and help these areas kind of grow?
Yeah, well, I guess you can see the work that Romalya is doing and how important that is. So we've got these technologies that work in the lab, and that's very exciting, but really we need talented engineers who can help us understand what this looks like as we scale up or whether scale out. There's many ways of achieving this, and then to start to understand and optimize these processes. So there's always a new material, there's always a new catalytic reaction, and that's what Akshat and I live and breathe. But we need direction. We need to be able to prioritize what it is that will contribute most to solving this problem.
Thanks for that, Matt. Romalya, do you have any input or insights?
Yeah, I think Akshat and Matt know better about how the students can make an impact. But like Matt said, joining parts of projects that you're passionate about would be a way to start.
Okay, awesome. Thank you. And then I guess we just have one last question before we finish up. So this last question is, how about throwing the CO2 in natural gas voids? I guess that is as we use more natural gas and those kind of wells become empty, would those be viable spaces and options to kind of dump our CO2 into?
Well, that's sort of that's something that's been considered for decades. I have to admit I'm kind of ideologically opposed to sequestering the CO2 because then it's always a cost and it will always be resisted against the capture. And I think if we turn it into something valuable, you totally revolutionise the whole process. If you're talking about sequestration, the key thing is not so much the space underground, it's the geological formation. To Akshat's point, once you put it there, it has to stay there. So a lot of natural gas wells may be unsuitable for storing CO2 over geological timeframes, but there are plenty of underground formations and plenty of trial sites in Australia, in fact, where we're doing these tests. But at least in my view, CO2 is a highly valuable molecule, and having gone to all the trouble to capture it and separate it instead of burying it in the ground. We should turn it into something else. You know, even if tomorrow we stopped all hydrocarbon-based oil and gas and coal, we still need hydrocarbons to make medicines and polymers and clothes and all these sorts of things. And so we still need a source for that. And so CO2 conversion is critical to all of that.
Thanks, Matt. I think that's a good point to leave on, the value of CO2 in ensuring that we can continue to produce some organic molecules for the future. So that'll be it for the webinar today. Thank you everyone for coming, and thank you again to our three panelists for taking the time out of their busy schedules to present today. We will have another webinar next week on the biological routes to converting CO2. So please register and tune in. And we also have our carbon hack coming up next week as well. So if you are interested, make sure to submit an expression of interest. Watch out our website because the recordings for our webinars should be online shortly as well. Thank you again for everyone, and I hope you were able to get some experiences and some new information out of this.
Thanks, everybody.
Thanks, everyone.
Thank you.